Sure. Is this on? Can you hear me? Okay.
If you have any questions,
Okay. Okay. Yeah. I've got a skewed distribution here, so I'll move over to this side of the room. That's okay. I can deal with it. I'm a statistician. I can deal with this. Yeah. So I wanted to talk today a little about the logic of how it is what these hypothesis tests are doing behind the scenes. And I chose this because it's where most people get lost in statistics. And if you don't understand this part, you don't understand much at all about statistics, really. Inferential statistics, anyway, where we're actually testing hypotheses and having p-values and confidence intervals and such. So I like to think of hypothesis testing as a signal detection task, where in this case, the first example I give is going to look at the mean of two groups. So what it does basically is compare the difference in means, the between group variance, to the between group variance, the background noise or error, to see if it can detect a signal relative to the background noise. And the goal of the reason we teach research design methodology is to refine the signal to noise ratio. So we want something that looks like this rather than something that looks like that. So we have a whole science dedicated to yielding this, the way that you actually collect your data, design the study and collect your data. So the general form of a parametric test, and we'll talk about parametric versus non-parametric pretty soon here. But the general form looks like this. We're looking at a signal to noise ratio between group variability, i.e. in this case, mean differences, relative to background noise, or what we call more commonly error in the data, just scatter in the data due to differences in the subjects we have in the sample. So under the null hypothesis, where we have, that means typically a null hypothesis means no difference between groups. That's what we anticipate. That's the baseline condition. The expectation, that's what the big E stands for over the long run. The expectation of that ratio is equal to 1. If we ran a study many times, analyze the data, and in fact the null hypothesis was accurate, there is no difference between groups or between treatment conditions, we would on average excuse me, have a ratio of 1. The between group difference should not on average exceed the within group difference, the background noise. So we test the null hypothesis against an alternate hypothesis, which is typically there is a difference between groups, or there's a difference between treatment conditions. And we hope to find that, in fact, the ratio of the between the two within is greater than 1, significantly greater than 1. So that's what I want to talk about. What does that mean, significantly greater than 1? So this is an example of a small signal to noise ratio, where the signal, the distance between two means, the means of the two groups is approximately equal to the background noise within groups. That would be where it's very hard to detect the signal relative to what's going on in the background. This is what we hope to find, a large signal to noise ratio, which yields a small p-value, a significant p-value. So we want to find something that looks like this. And again, this is in the service of the research design aspect of our study. So you see here, I've displayed these as these nearly perfect curves. Do you ever see data like that? Not even close, right? I mean, this is what I see. This is a nice study. It's actually a study of weight loss. and this is one group. It's called a histogram, where we plot the frequency or the count on the y-axis against the outcome measure, weight at the end of the study. And I'm going to simplify this design for purposes of this presentation, but it's the count plotted against the value that we collect, the outcome measure. And this is a table one, a classic table one, abbreviated. Heated a little bit because I said, okay, let's ignore the pre-weight, the pre-study weight, because it's equal. It's exactly equal across groups. So we're going to be focusing on the post-intervention weight for two groups, the bariatric surgery group and the medical treatment group. So we enrolled these patients. Half of them received bariatric surgery and half of them received medical treatment. They differ a little bit in terms of the sex distribution. The age is roughly the same. So we would consider in this instance, in this fake news instance, that we've established ceteris paribus, right? All things being equal across groups, except for the condition. One half of the patients got surgery, one half got medical treatment, which consisted of counseling, dietary recommendations, enrollment in Weight Watchers if they chose. This actually took place, but I've extracted a subset of the data. We actually had like 700 patients in this study. So the question that we're asking is, if you see right here, at the end of the study, we have a 10-pound difference between the two groups. And the question that we're asking is, what is the probability of finding a difference of at least 10 pounds between groups if, in fact, the treatments were not differentially effective? If bariatric surgery was not better than medical treatment, or medical treatment was not better than bariatric surgery, on occasion we're going to find differences between groups. Always. It's never going to be exactly the same. So we're focused on what are the chances that we found a difference this large between groups if, in fact, the treatments were not differentially effective. Does that make sense? So in this case, I'm going to use an independent samples t-test. I wouldn't in real life, because I would have to account for the differences in pre-weight, sex, etc., a lot of things that we would enter into the equation as what we call covariates. So here's my histogram of the bariatric surgery group. 185-pound mean weight at the end of the study versus, I've overlaid here a histogram of the medical treatment group. And you can see that they tend to be slightly larger than the bariatric surgery group. Is there a difference? Does that difference appear to be meaningful? Yeah, well, we've got 100 people though per group. So we've got some power to find a difference, even a small difference if it's there. So yeah, but you can't, I mean, what could you say? This is a descriptive question. We can publish the means and standard deviations, but we really haven't yet addressed our research question. Is bariatric surgery differentially effective from medical treatment in terms of weight loss? So we don't know. All we can say is the means are or aren't different across groups, but that doesn't mean anything outside of that sample, outside of the context of the study. It's just an observation. But what we're interested in is an inferential question. Is the difference meaningful in a population from which this sample was drawn? So then we can say, we can go to press and say that bariatric surgery results in a larger weight loss than medical treatment 6 months post-intervention. So the question we're asking is inferential. It's a probability question. So that's why we resort to these distributions, probability density functions. These are what we're going to compare in the theoretical sense. And then we can derive an answer that can be generalized from the sample to the population, assuming we do everything right. And we're focused here at this point on the between group differences, the size of the difference or the width of the difference, the interval between the mean of the bariatric and medical treatment groups. So to answer these questions, and this is where a lot of people got lost in intro stats, where they didn't make the leap. What we need to do is now apply some assumptions to the data sets. So we focus on a theoretical distribution of sample means rather than looking at the raw data. We abandon the raw data at this point except for two summary statistics, the sample means and the standard deviations. Does everyone know what a standard deviation is? It's kind of approximately the average absolute distance between the mean and each of the data points. It's the average distance. Getting rid of the valence, the absolute difference. So what we do, and we don't do this literally, the computer does this, statisticians do this, theoretical statisticians do this. Based upon those two statistics, we're able to create a theoretical probability distribution of means, not raw data, but of means, because we abandoned the raw data at this point. We don't care about it except to check to see that we've met certain distributional assumptions. So the data points that comprise our theoretical distribution are based on the notion that we could theoretically draw a very, very large number of samples, same size samples from the population from which we've chosen our samples and construct a distribution or distributions possibly of sample means, like a histogram of an infinite number of means calculated from an infinite number of same size samples, 100 people. So going back to this notion of signal to noise variability, what's our between group variability? How would we express that here? This is our numerator for our test. What's our best estimate of between group variability? 10 pounds on average. So that's what enters the numerator. The denominator is a function of within group variability, the noise, signal to noise, the noise portion of it. The only thing we have at this point is we have standard deviations for both groups, which I've set to be equal, just to make things simple. So some of you may have seen this before. But it's something that I use in class. And he told me I had to stop share, and then I need to switch to this, and then start share again. Is that the case? I want to share this. Good. Okay. Have you seen this before? Anyone played with this before? So what this does, this is intended to give you an idea of what this theoretical sampling distribution of means looks like. And there are sampling distributions for every statistic that we have. This is the mean. On this one, we can actually, in fact, I'll do it now. Here we're going to look at the mean. I'll put the median up here against it. So the way the math underlying significance tests works is we assume that we could theoretically draw an infinite number of samples and then plot their means. And we're interested in the distribution. We're interested in where the mean falls in the distribution, the theoretical distribution, and we're interested more specifically in the dispersion of the distribution, because that's how we're going to figure out if the distance between means that we found is meaningful. So the way this works is I can do this. You see there what I've done is I've drawn 2 samples, each one of 5 people. And then I plotted the mean for each of those. So I can do that again. I can do that as long as I want to, but you're going to get bored pretty soon. So I can speed things up here. I'll draw 5 samples. And you can see what's happening right here is that it's forming a distribution of means based on samples of 5 apiece. So I can go on, and it's forming a distribution of the means, a sampling distribution of means, and a sampling distribution of medians. And they're roughly the same right now. So let me kick it up a little bit. And I say I drew 10,000 samples. What do you notice about those 2 distributions? Or either one? Yeah, and they're approximately normal, right? And that's based on the central limit theorem, which is actually what got me interested in statistics. It's magical. So we draw a distribution of sample means, we plot them on the 3rd graph down, and it magically becomes symmetric and normal. What do you think will happen if I choose a uniform distribution that looks like that? Where we just have everyone's responded exactly the same way. The weight gain, weight loss was exactly identical for every patient in the study. What do you think will happen down here if I draw the same distribution of means? That's what you'd think, right? But based on the central limit theorem, there are several assumptions, but the central limit theorem says that the mean of the sampling distribution of means is going to be equal to the mean of the population, which is crucial. Otherwise, we have nothing. And also that it's going to be normal. So if I start with a uniform distribution where everyone lost 180 pounds, and I do this, I get a normal distribution. Now, the one catch here, and we'll talk about this in a little bit. So I can do this till the end of the day, but I don't want to do that. So let's look at a skewed distribution. You know the notion of parametric versus non-parametric statistics and fitting the model to the data. Well, watch what happens if I have a skewed distribution like this. What happened? It's trying to normalize it, but it's not perfect. And in fact, look at the difference between the distribution of means and the distribution of medians. This is why when we have a skewed distribution, we use inferential statistics that look at the median rather than the mean. The mean is a misleading estimate of central tendency. It's slightly skewed to the right. The median is a more accurate estimate of central tendency, of the center data point in the data. So that's why we use, I'll show you what we do with that. But does this make sense, kind of what we're doing here? That's how we construct, and we don't literally, we have formulas and algorithms that do all of this for us instantaneously. But the sampling distribution of means is the theoretical distribution of a very, very large number of same size samples from the same population, drawn from the same population. And you see a distribution to them. They're not all equal to 180. You're going to have outliers, potentially, but not if it's infinite. Everything's going to come together at that point, and you're going to have a perfect normal distribution. Any questions about that? Yeah, let me stop that now and switch back to share. And I want this, I think. So obviously we couldn't possibly have access, we can't construct our own sampling distribution. So we estimate the shape and form of the sampling distribution based upon the nature of the data, the mean specifically and the standard deviation. And in fact, we estimate this, we estimate the dispersion of the data in the population from which the samples were drawn using a statistic called the standard error of the mean. That's what goes ultimately into the denominator of our signal to noise test, the standard error of the mean. And we constructed this simply. It's the standard deviation of the sample divided by the square root of n, because we have, I have not, but someone has shown long ago, in fact in the 1920s, that the sampling distribution of means is an inverse log function of the standard deviation for the sample based upon the size of the sample. Pretty elegant. But it's accurate. So that's what we use to estimate the standard error of the mean. So you all are familiar with something like this, right? The standard normal distribution, where we break it out into standard deviation units, where we say that between -1 and +1 standard deviation units, we have 68% of the population in a normal distribution. And we have 95% between -2 and +2 standard deviations. Does this ring a bell from intro stats? Yeah. So this is what we use to determine the degree to which our data differ from a normal distribution. But watch this. See, I've got, these are standard deviations. This is the standard normal distribution. When I do that, the distribution of standard errors of the mean is exactly identical. Exactly identical. So everything that holds for this, the density functions for this, we can apply to the standard error of the mean. So we can then calculate how far apart two means are in standard error differences. And that forms the basis of our inferential test. Because we know that a mean of one standard error difference is pretty substantial. A mean of two standard errors difference would be huge. So we use that information to form our test statistic like this. So we have two groups. We estimate the width of one standard error by taking the standard deviation of that group divided by the square root of n, because again, it's an inverse log function right here. And then I need to pool the two because I've got two groups. So I have to take the variance. I have to square the standard deviation, add them up, run this calculation on the two, then take the square root of that, which gives me a standard error of the mean of 2.83. That's my noise, my background noise, in the population, not the sample. It's an estimate of background noise in the population. I have my between group variability of 10 pounds. I have my within group variability. One standard error is equal to 2.83. Then I form my test statistic right here. Does this all sound familiar? So this is an optimal way of estimating the dispersion of my sample data in the population, assuming an infinite or very, very large number of replications of my study. I'm stating that, in fact, this is the way they are dispersed in the population, which is how wide one standard error is. It's one standard error difference is 2.83 pounds. So you see how I can build on that then to say, okay, well, I found in my two groups a difference of 10 pounds against background noise. So I've got 3.5 standard errors difference in my two groups, which is 3 units. That's enormous. In terms of probability function, it's enormous. So the old way, any questions on that? So let me jump to this and then I'll come back. So the old way of looking, this is the way I learned, was we took our t-value of 3.53 and then we went to a lookup table. After doing this all by hand, you go to a lookup table and you identify, you want to do a two-tailed test, which is alpha 2. I'm interested in the significance level of 0.05. So I calculate my degrees of freedom here, which is 200 minus 2, 198. And I look down this column, an alpha of 0.05 to reject my null hypothesis. I look all the way down here and I find that in fact, I have exceeded the critical threshold in order to reject my null hypothesis and claim that I have found a statistically significant difference at the level of 0.05 two-tailed. In fact, if I look over here, I find that I could reject this hypothesis at a level of 0.001 two-tailed if I chose to. And this is what the output looks like, where in fact, this all software anymore calculates an exact p-value. So I find when I put these data into a program, run an independent sample t-test of 2 means, I have a p-value of 0.0005. So 5 in 10,000 chances of being wrong in rejecting my null hypothesis. So what that means here, a p-value of 0.000005. That's an index of the certainty with which I can reject the null hypothesis. And it means very specifically this. Assuming there's no difference between groups in the population, and again, it's the population. We're not interested in the samples anymore because we've made the leap. We've switched the flip. We've made the leap to inferential statistics. So assuming there's truly no difference between groups in the population, what's the probability of selecting samples just by random happenstance that displayed a difference of 10 pounds or more? It's not going to happen. 5 in 10,000 times it's going to happen. So I'm relatively certain that I have not made a mistake in rejecting my null hypothesis, i.e. concluding there is a difference between groups. There's a difference between bariatric surgery and medical treatment in terms of efficacy for weight loss. And conventionally, we rely on a p-value of less than 0.05, a 1 in 20 chance of being wrong, to say that in fact, we have found something here. It appears that bariatric surgery is better than medical treatment, at least in terms of weight loss. So anymore, it's very rare to see a p-value stand alone. Almost always, in journal editors and reviewers insist, almost without exception, that you associate the p-value with the confidence interval. So you get the test statistic, be it a mean, a median, an odds ratio, relative risk hazard ratio. You will almost always see a 95% confidence interval associated with that test statistic or summary statistic. So what a 95% confidence interval means is that if we drew the same size sample many times over from the same population, that in 95% of those cases, the truth, the population parameter would fall somewhere within that confidence interval, within the range of that confidence interval. And we use them for everything: means, proportions, effect sizes of all sorts. And they look like this. So here they calculated a hazard ratio, looking at, it's comparing two relative risks, and they give you the hazard ratio as well as the 95. They're saying our best guess is that the rosuvastatin yields the primary endpoint, whatever that is, about half the times that placebo does, i.e. it's protective. But we think it's about 56% of the time, but truly it's somewhere between 46% and 69% with 95% certainty. It's somewhere within that range. The confusing thing about this is the truth, the parameter, the truth in the infinite population is fixed. This is what floats around depending upon the makeup of our sample and the way in which we administer the treatment, measure the outcomes and such, define the outcomes. So we're saying that this, really a better word is covers. We could say that this confidence interval covers the truth 95% of the time. And sometimes you'll see some really impressive statistics, results of statistical tests with huge confidence intervals ranging from 0.15 to 13.2. And yet it could be, with a large enough sample, it could be statistically significant. So you always want to look at not only the summary statistic here, or the test statistic, you also want to look at the confidence interval, which tells you this is the range within which it could be as low as 46, or it could be as high as almost 70. It's somewhere in there. This is probably our best approximation right here, the midpoint of the confidence interval. And that is a function of the standard deviation of the samples. So any questions about that? I gave you a quiz. Do you have some sense of how these distributions work, these theoretical sampling distributions work? And there we have them for means, medians, correlations, effect size. We have everything has a distribution. And if we know the algorithm, the way to estimate the sampling error, we can do it. And then we can then conduct p-values, and we can construct 95% or 99% confidence intervals. It's all simple math from that point forward once we've identified a proper model and a proper algorithm. And speaking of which, we use algorithms, mathematical algorithms, to estimate, to give us our best estimate of the between group difference and the within group difference. And for parametrics tests, we make assumptions about the distribution of those data in the population. For many types of data, we cannot fairly make assumptions about their distributions in the population. We just simply don't know what they are. This is a family of distributions for univariate data. We've been talking about the normal distribution, but we actually have access to many, many more. And we can pick and choose among these. There are tests to say, you don't really have a normal distribution. Your data does not exhibit a normal distribution. It's a gamma Poisson, it's an inverted gamma, it's a chi-square, hypoexponential, et cetera, et cetera. And all of these are associated with a different algorithm to optimize our estimate. You just have to choose the right distribution. And again, these are only univariate. When we get into bivariate distributions, where we're looking at two variables, two data sets at one point, paired data sets at one point in time, things then get complicated, very complicated. But this is what computers can do for statisticians. It's just incredible. When I was learning this stuff the first time, it was a normal distribution or you're screwed. You know, that was basically it. And now we have access to all this stuff, and it's instantaneous. So the difference between parametric and non-parametric tests is underappreciated. For parametric tests, we have certain distributional assumptions that we adopt, and we can test those, and we can look at the frequency distribution, the histogram, and make a good guess as to what fits the data, what model best fits the data. So we're not cheating when we calculate a p-value. So these are examples. We just did a t-test. These are examples. Things can get very complicated, multidimensional, multivariate, with many predictors in the equation if we want. So you've probably seen some of these reported in literature. non-parametric tests make no assumptions about the distribution of the data underlying the sample, i.e. the population distribution of the data, the theoretical population. So you've seen certainly chi-square is the most commonly used statistic in scientific publications, probably followed by t-test or a Pearson correlation. You see I've got a Pearson, which relies on a linear assumption, and a Spearman, which relies on a monotonic relationship. You see an increase, but not a linear increase as you go across the data. So we have all kinds of tests, and this is probably 2% of the tests we have access to. But this is what you see until you get really complicated, and then things get, I could have talked about those for the whole hour, but Nate made no sense of them. So the way we choose whether to use a parametric or non-parametric test, these are kind of guidelines. And there's some leeway and flexibility, but we can use parametric tests if we have interval or ratio data. The sample size is at least 30, and the data conform to a known distribution. It doesn't have to be normal. If we can specify, if it's a Poisson distribution, if it's a gamma distribution, we can specify that, as long as the program knows what you think the underlying data look like. Non-parametric tests, which tend not to be quite as powerful in yielding significant outcomes, we tend to use with ordinal and nominal data, rank order data, categorical data, samples under 30, and the data do not conform to a distribution. We don't know the population distribution of these data, or as you saw when I was running that application, you know, it would not be a good idea to apply a parametric test based on a normal distribution and calculate the mean when I have a skewed population distribution, because you saw the difference in the two. It was substantial. So you need to pick the right test. And I just wanted to give you an example of a classic non-parametric test, and you can see how it works. So this is called the Mann-Whitney U. It's one of a whole family of what we call rank sum tests. So what we do, I have a control group and a treatment group, and I have a set of scores from each. We combine all the scores into groups like this. So we put the treatment and control groups together in one column. We rank order the scores, and then we assign rank numbers to them. And then obviously in a data set like this, you're going to have a lot of matches, a lot of duplicate outcomes. So the way we handle that is we calculate the average rank, just like this. So we had 4 subjects who received the score of 1. So we give them all of them a mean rank of 2.5. So I could combine the whole data set here, and you can see I've just expanded that last table, and I've rank ordered them like this. I've then given them a rank order based upon replications of the same number. And then I calculate the sum of the ranks for the treatment, 70, and the sum of the ranks for the control. And then I calculate the mean rank. And guess where I go from there? I've got 2 means to compare again. But I have to rank order them because these are rank order data, so I can't assume that there are equal intervals between the data. All I know is that 3 is higher than 1. I don't know that the difference between 1 and 3 is the same as the distance between 3 and 5. So it'd be cheating to to assume that these had equal intervals. So the way I handle that is I rank order them like this. I don't rank order them, the computer rank orders them. And then it compares the mean ranks and says it's highly unlikely that you're going to get a distance of 7 to 14 in mean rank if in fact treatment is not better than control or vice versa. And it gives me a p-value right there. So the same sort of output, and I can calculate a confidence interval for a Mann-Whitney U also, or a Wilcoxon test. I can do the same thing, but it's based on the same logic. Again, it's the signal, the distance between groups, relative to the background noise, signal to ratio. That's what inferential statistics is all about. Did any of this make sense? Sort of? You have to go through it a couple hundred times and then you say, oh yeah, why didn't I get this the first time? So that's all I have. I was anticipating a whole bunch of questions. There we go. Is there anything I can clarify? But again, this is where students get tripped up. In the leap from descriptive statistics are very straightforward and simple to calculate, but when you make the leap to wanting to generalize the results of the sample data to the population, then things get complicated. And you have to have the right model. And you have to run the right test and then interpret it properly. I'll repeat it.
How do you already make determination on what is the best test to use?
So, yeah, so the question was, given the number of distributions and types of tests that we have access to, how do we choose which one is appropriate for our data? And the first thing you do is you go back and look at the literature. And you find out what assumptions previous researchers have made concerning the population distribution. Because you really can't glean that very well, especially if you have a small sample. You really can't eyeball it and say, or plot a histogram and say, well, this is a normal distribution. I go back to the literature and I say, people who've used this outcome variable in the past, what do they tend to rely on? Do they make the normality assumption, which makes my life a lot easier? Or do they, is there some more complex distribution underlying the data in the population? And we can, in fact, recently, about 3 years ago, we now have the availability to combine these darn things. I can put 2 or 3 distributions together for one data set and say, this is the low scores form a normal distribution, and then I've got these high performers who have a very skewed distribution to the right. I can do that, which is ridiculous. But we rely on the literature. There are software programs which will do a best fit analysis. So they'll look at, you feed them the data, they'll look at the distribution, they'll say, this is probably a gamma or a Poisson or it's normal. And then you have to make the argument ultimately that you chose the right distribution. In terms of picking the right test, that's a function of sample size, the nature of the data, be it nominal, ordinal, interval ratio, how many people you have, how large your sample is, and your model, your data model. Are you going to look at just the difference between 2 means, or do you need to also consider baseline weight? Do you have to consider male versus female? You know, as you pile in more covariates or more predictor variables, things get more and more complicated. And at some point with a small sample, you've exhausted your power. So you have to be very selective about every variable you include in the equation costs you in terms of finding a p-value less than 0.05. And also you have to look, does it make if I include male, female in here, does it make my confidence intervals smaller? Because that's what I'm after, small confidence intervals, which are associated with small p-values. So you play around. I mean, you have to, in the best of studies, you file a statistical analysis plan and you say, this is what I intend to do. And because I've looked at the literature and that's what they did. Well, yeah, exactly. And then you rely on, yeah, You look at what other people have done. And then once, you know, if I were involved in the clinical trial and I filed a statistical analysis plan with the FDA, there's no backtracking from that. That's what I'm stuck with, period. So I try to cover all my possibilities in that analysis plan and say if the data are shown to be normal, if they're shown to have a right skew, alternatively, 60 pages before you're done.
Another question, in statement and maybe even some public claiming that, you know, matter for has been published before some research area might be incorrect because how would you go back to a lot of manuscripts and revise it more appropriate statistics?
Yeah, that's a tough call. The question was, what if we, in terms of relying on the literature, what if we go back and look at the literature and find that, in fact, they use the wrong statistics or the wrong distributional assumptions? What we have to do then is we have to make an argument that they use the wrong distributional assumptions, they use the wrong statistical tests. And more often than not, they did. I mean, that's why in terms of looking at the literature, checking the background, I rely on New England Journal of Medicine, JAMA, Archives of Emergency Medicine, the top tier journal, because you know their statistics were right. They've published 7 different meta-analyses, meta-analyses on validity of statistical methodology in the top 10 journals, in the medical journals in the country. 70% of them are invalid. 30% of them are valid. When you have an expert statistician review the manuscript. Now they have not published one of those in years. I think it's gotten a lot better, but I had 7 of them at one point, and the average was, they said between 30 and 60% of them had valid statistics. Of course, that was before we had access to all these options. So you can customize your test and your distributional assumptions to, now we can customize them. I can choose one of these. And, but yeah, you hate to go and say, well, they did it and everyone relies on this journal, but they were wrong. That just gets you into trouble. That's not a good way to go. So it's, yeah, you poke around and you see, well, what's conventionally commonly used, and do my data match up with that? Can I justify using that type of approach to the analysis? So it's not clean, it's not clear cut. It's more art than science in that, I think. Okay. Any other questions? Okay, well, thank you very much.